conditions seem to be ideal for that expansion, where you've got good soils and good precipitation, and everything's just right. And it's really frustrating to try to come back and get a handle on those.
And now juniper is encroaching in a lot of areas in Oregon, Idaho, Northern California, where it wasn't that present before. Reynolds Creek is in a supreme situation to be able to monitor the invasion of juniper, with the idea in mind that there are 3 phases to juniper invasion. The first phase would be if there's just a little bit of juniper seedlings around, and there's a few old growth juniper. The second phase would be where the juniper is actually starting to encroach, and you can see more in the landscape. And the third phase, of course, is where juniper has taken over, and the land below the juniper is no longer able to produce anything because juniper is sucking all the water out, and there's no opportunity for other vegetation.
The stage 3, we're not to that point yet, but we're definitely into the early part of the stage 2, where you have the few of the older growth, but a lot of the younger, within the last 10-15 year growth, junipers coming in, plus up to present.
So what we're suggesting is removal of juniper and then reintroduction of fire to get these systems back on a natural order, where juniper expansion is controlled when they're in the young expansion stage and are still burnable when the rest of the system burns. Well, the Reynolds Creek Experimental Watershed is the reason we are here. It was established as a research location by Congress in 1959. The original intent was to look at hydrologic processes and weather and climate distribution over complex terrain in mountainous areas. We were picked to represent the intermountain semi-arid rangelands, and we were picked because our primary precipitation input is snow. Since 1960 we've been collecting meteorological data and stream flow data and vegetation data from Reynolds Creek. After maybe 20 years, we refocused from evaluating general climatology of the basin to using daily and hourly weather inputs to model hydrologic processes. Most of our hydrologic program here is based on snow hydrology. You've probably noticed when snow falls, it doesn't necessarily stay where it falls, it blows around and drifts, and the pattern of redistribution in drifts determines how runoff occurs in the spring.
Every 2 weeks we go and service our weirs, and a weir is just a way in which to monitor the water that's flowing through the weir. And what we do at the weir is we take measurements as to the flow of water that's coming out. It's very important for us to take redundant measurements because we want to make sure that our data is of the highest quality. This is called an automated water collection system, and what it does is, depending on how it's programmed, it'll collect water from the creek itself. There's a line that goes out, tubing lines, out to the mouth of the weir. It draws water in here when it's programmed to collect a sample, and then it fills up to 24 bottles in this lower section. We've got 2 of these, so we can have a capacity of 48 bottles. And what it does is, depending on the water tank that's coming through, it'll actually collect a sample. Or if the hydrograph, or the amount of water coming through, rises a significant amount over a period of time, then it'll automatically collect a sample as well.
You really need a very long climate record to understand anything hydrologic. There's a lot of variability from year to year. We're also interested in processes of global climate change, and in order to document those changes and their impacts on hydrology and rangeland resources, you have to have a very long record. In order to tell how much water is flowing in the stream, all you need to know is the height of water in these weirs. So we have weirs that can handle up to 22,000 cubic feet of water per second. We have smaller weirs at higher elevation for lower flows. We're very interested in modeling how the distribution of snow affects water supply, which is a huge issue in this region. Most of the water we have for agriculture and water that flows into rivers around here is from snow melt. And because snow has such an uneven distribution when it's deposited across the landscape, we're trying to improve models for predicting things like the amount of water in a reservoir for agricultural purposes. Historically, Reynolds Creek was set up to look at precipitation distribution in mountainous terrain. When they originally set up this watershed, we had a rain gauge every square mile out at Reynolds Creek. Our rain gauges are a little different from other people's rain gauges. Most rain gauges have a shield on them to break up the airflow so that things like snow will fall in our gauge rather than just blow over the top of the gauge. We determined a while ago that all rain gauges undercatch snow, so we put out 2 rain gauges at each location, one with a shield and one without a shield. The unshielded gauge measures less snow, but what we believe actually hits the ground is related to the difference between the shielded and unshielded gauge. It used to be we would only have full meteorological measurements at a few sites throughout the basin. They're very expensive and historically have been more difficult to measure things like humidity and wind, solar radiation. But we've since reduced the number of rain gauge locations and increased the number of meteorological stations. So most of our full met sites now have a full suite of meteorological instrumentation.
Well, this is one of a number of sets of rain gauges we have at the Reynolds Creek Experimental Watershed, with the idea in mind that this will measure the precipitation that's falling, whether it's rain or snow. What we found in the past is that you'll notice that there are 2 types of gauges, the shielded gauge or the unshielded gauge. The unshielded gauge reports an undercatch just due to the fact that when you have rainfall, it also produces, during that time, is a storm probably, and so the winds are keeping the rain from falling down into the orifice of the opening of the rain gauge. So we put shields around, and the shields actually counteract the effect of the wind. So much so that if it's a shielded rain gauge, you actually get a number that's a little bit higher than the actual fall that came onto the ground. So what we've determined is that by using a number that's somewhere between the undercaught unshielded rain gauge and the overcatch of the shielded rain gauge, we can come up with a number that's very accurate. And so what we've done from that is determined a formula, if you will, so that we can just put out one shielded rain gauge and then adjust that number to give us an actual more accurate catch for the precipitation that's fallen.